Okay, then what we really need to do is interpretation is a very important part. Okay, then we say what are the methods, okay, that we can estimate the fugitive emissions. These methods are called upward flux method, and we'll explain as to how this is used. We also use a method called, you see here, DW and UW. This is essentially referring to downwind upwind method, that also we'll see. There could be another method, something like Cauchy, stack or roof monitoring. Suppose you have a large room and there are the ventilators on the top of the room, and then that's where you are having the fugitive emissions. To give a little typical example of the Cauchy or roof monitoring, sampling through the vents or temporary hoods, you can provide the temporary hoods that you can do. So to give a little example, if you can, maybe you can recall or correlate, is the cement, let's say cement packaging. In a little closed room with the top there can be little openings, and then you can go and take your samplers on these openings because emission will occur from those openings, and then you can do the Cauchy, stack or the roof monitoring. The standard method for the road emissions, because you might have observed when the industrial the roads are quite dusty, and as the trucks which is carrying the raw material, which are carrying your end products and the raw material, as they move onto the road in the industry, they cause significant emissions. So there is the method to how to estimate the emissions from the road dust. So as I said that I'll explain you the upward flux method. The method is very simple actually. You have to take the area into the consideration. That area you see here, if I can draw this is the area, and then if you can somehow on the top of this, if you can measure the upward velocity through a small handheld anemometer. You can measure the velocity using a anemometer and or the other stuff. So you can find out what is the velocity of the air, that is vertical or vertical drift, and then simply you multiply the area versus the velocity of the updrift, and then you can find out the the emission that are occurring. Little example here. So you have to measure the particulate concentration here. So here you see here PM concentration, that may be units may microgram per meter cube. Then you need to know the area that is under consideration, okay, that's multiplied by the area, and then finally you also multiply by the velocity or the upward velocity or the vertical drift. Velocity here is not horizontal wind speed, it is a vertical drift, if I can use that word term here, vertical drift. Okay, and then there are the unit conversions here that is required here. This you should read this as 3.6 into 10 to the power minus 6 actually. So this is really minus 6. The more like unit conversion, and then you can get the emission rate in kg per hour. So simple method. And now let's talk about the other method. So wherever you are discharging the pollutant from the top, or a confined area where the pollution is likely to rise, you can use this particular method, and that's frequently used with this method. We also use the method, the downwind upwind method, or the what I had described in my earlier slide was downwind upwind. Maybe I use this way, downwind and upwind method. So what you see here is that this emission is occurring, okay, they are not quite vertically, but they are a horizontal emission. So what you do here with the source, you and suppose the wind is blowing like this, okay, and so you are doing the measurements of the dust in the, so this side is your is your downwind, okay, and this side is your upwind. So what you will see is the emission is impacting this side. So you can measure the concentration here. Let's say call this concentration as C1. You can also measure the concentration on the upwind side. You can put a device here to measure the upwind concentration, okay, and let's call this as C2, okay. And what you would see here, the C1 will be higher or likely to be higher or should be higher actually. So this C1 is apart from the background, this is the background and the impact caused because of the source. So here is the total impact, the background plus this thing. So if I can define this C as a concentration which is the difference between C1 and C2, that is my C1 and C2 are measured. So the difference in the concentration I will see that as the impact or the contribution caused by the source under consideration, which is a fugitive source. So you can see here the C, and this C is related to the emission, okay. The Q is the emission from here. If I can say here, Q is the emission rate in mass per unit time. So this is the C is this is what is measured, okay. This is U is nothing but wind speed, and that you measure on the field. Here this is a little wind speed measurement. In situ, it's important that you do the in situ wind measurement, okay. That's important that you do in situ. And so the wind speed is known, and then sigma y and sigma z are the dispersion parameters that you can get from the literature as the which are the function of the distance. So depending on the how far your distance that you have measured, sigma y and sigma z are the dispersion parameters. So if I can show you here that if you have the emissions which looks like this, okay, and if I take the section and look through the emissions here, okay, I'll see that the plume will look like this, okay. So dispersion onto this side, the measurement of the dispersion onto this side is, that's what we call as the sigma y, and this we call as the sigma z. And these things will become more clear when you learn more about the dispersion modeling. But dispersion modeling is a simple thing. You can apply sigma y and sigma z you can get from the literature, and what is really unknown is the Q. So now in this exercise to find out the emission Q caused because of the transport or for the disposal, I won't call it disposal, but handling the raw material, is the emission is Q. So that this is let's circle those things which we know. So we know the C because that we have measured on the field, pi is known, sigma y is known, the U is known, the sigma y is from the literature, sigma z is from the literature, and what is really left unknown is the Q. So one can estimate the Q. Simple technique but useful technique, so that you can find out the total emission which is caused because of the handling of the raw material or the tippling. This is called basically wagon tippler area. So when the coal dust is being tippled and there are the emissions, one can very easily find these emissions. Okay, very quickly, what you have is the source. Okay, the source here, you have to do the measurements in the downwind, you do the measurements in the upwind, wind is blowing like this, measure some meteorological parameters in situ, okay, that's to be seen here, and the C1 minus C2 is the impact of the emissions from the source, okay, and that is related to the total emission rate from the source times divided by pi u sigma y sigma z. U is the wind speed you are measuring, sigma y and sigma z are the dispersion of the pollutant plume in y and z direction, and therefore which is function of the distance, don't forget that, and you can find out what will be the Q, and then Q can be estimated. Okay, let's further go and see how one can estimate the road dust. Okay, the picture here you see is that how one can estimate the emissions that will be caused because of the movement of the vehicle onto the road, because this can be a major source both in the urban area as well as in the industrial area, because lots of trucks are moving. You see here we want to find out the non-exhaust road emissions, you see, and this typically the situation we find a lot in our Indian conditions. So you see here there is a little tempo that is going on the kind of unpaved road or partially paved road, and this is the paved road, but a heavy traffic is there, and then as a result we want to estimate the emissions from this one. The fugitive road dust emission is important, as you can see here. So how this is done? Okay, so first of all what you do is that you do the dust collection across the road. Okay, and how the dust collection is done, this is through the picture it is shown here. What you see here is this is the road. You take some strip of the road, okay, and find out and what is really you are interested is the cleaning this road, okay, and then you see here this is a vacuum cleaner, okay, and there is a little bag here, not so little either, and in the bag the dust will be what you have sucked through is collected here, because there is a filter here, is a bag, there is a filter here. Then what you can do is, once you collect the dust on a particular area, don't forget that we are referring to a particular specific area, as you see the checkered thing here, and that's what in every picture people are doing. Is this a little bit, I think this picture is from Bangkok, I'm not sure, but you see a little clean road and a little dirty road, but what you need to do is collect the pollution, the particles, dust from here, and then okay, then you need to find out, then you bring the dust in the lab, bring the collected dust in the lab and do some measurements there. What you need to find out is the silt load. Okay, before we start explaining you some more terminology, silt load, you sieve the dust that you have collected. The best way is to, once you have brought the dust, put down a newspaper and empty your bag onto the onto your paper or onto the newspaper. Take some part of the dust, pass it, weigh the entire dust, okay, and then find out the silt content in the dust that you have collected. This is done through the sieving. Okay, you can pass through a particular sieve. I think it is 200 mesh that you pass the sieve, and then you say how much was the content of the silt that was there. So and then units, don't forget that we had done the measurement on a certain area. So you see here the units grams per meter square. The units are grams per meter square. The silt load is known to you, okay, and W is the mean vehicle fleet weight. So you have seen how much the trucks are going, how much scooters are going, how much cars are going. So you can find out the mean fleet weight that is passing from the area that is under consideration. So this is again known, and K is a factor. Here you see the K. K is a factor that decides. Okay, you don't see here is a K. This is the value of K here. The K decides that what emission you want to find out for. You want to find out for PM 2.5. The K is 1.1. You want to find out for PM 10. The factor is 4.5. You want to find really large particles, then factor is 24. And be a little careful with the units that we have here. Is E is the emission rate of a specific particle size. Because why specific particle size? Because K is dependent on specific particle size. So whatever the value of the K that you want to use, you want to find out how much are the fine particles, that is PM 2.5. Then use the value of K 1.1, and then eventually what you can do is that you can estimate the E and the units will be gram per vehicle kilometer travel. Let's be very clear about this, that the measurement units are gram per vehicle kilometer travel, and because this is empirical formula, so you have to be very careful with the units, and you have to have the specific unit as defined here, and then you can't change the units on your own. Then of course you know the number of the distance traveled by the various vehicles, and then you can find out the total emission in terms of the gram of the dust is specific to particle size. So again, these techniques can be used, and they are all there in the literature. In fact, you can search through, and then you can find out at how this can be done. Okay, what are the range for the equation 1 to be valid that we just discussed? Silt load should be in the in this range. Okay, and what were the units for the silt load? Grams per meter square. So let's be very clear about this one, that we don't want units are fixed. We have no liberty, we have no freedom to change the units here. So the study part of the study that was done in the area that that study was done, the study we found that the silt load ranged between 1.8 to 77. So that was well within the. So what you see here is that mean vehicle fleet weight can be somewhere between 1.8 to 38 tons. In this study it was like this. Mean vehicle speed is in kilometers per hour, is should be between 16 to 88. In this study was 25 to 60. So we could use this equation, and apart from, so we could really estimate the emissions, but sometimes we also need to do some research in terms of really doing the relationship between the road and the tire that is particularly not applicable for the equation 1. Then we have to run this kind of test. What you see here is that there is a road drum, there is a tire, there is a weight that is put onto this one, and there is a pitot tube to see the velocity what is happening inside, and then you do the measurements inside this one, and you say, well, depending on the weight and the kind of vehicles that you have, that is will be determined by the weight, what will be the emissions that you can measure here. See, this study was done, you see here the road drum, and then vehicle, the tire was put onto this, and the emissions that occurred. So this is road, actually, if I can say bitumen road. Let's take this one, bitumen road, and experiments are done to see how much will be the emissions from here. So let's quickly summarize, especially for the power plant, what are the emissions that can occur, and those emissions which are largely of the fugitive nature, because we have seen through what happens to the chimney, but let's quickly look onto the what are the fugitive emissions. So let's go to the screen and see that what are the emissions that can, as a result we are trying to summarize the thing. So the wagon tipplers, the coal is brought down, okay, and a lot of dust emissions, okay. So that is what is called F1, that is wagon tippler. Here is a little mesh as they have, they'll kind of crush the coal, very primary crushing, okay, and then this is coal unloading and storage. So there is another emission that is taking place, and then you can also see the excess coal is stored separately, so that is another emission here, and then here is a conveyor belt, okay. From the conveyor belt there will always be emissions, the leakages, so that are there. Things are stored in the coal bunker and taken to the ball mill. So with the ball mill operations, like lot of dust is emitted, so the another source, and then finally it goes to the boiler, okay, that we have seen. So here the control, which is the particulate control, they are as it is being transferred here to the water, they are the leakages. So that you can call the source F6, and you see here apart from the regular source or the source from the chimney or stack is here, chimney, and you see apart from the chimney, which you observe very closely, the emissions which are the fugitive in nature are occurring all over the plant, okay, and we put a lot of efforts, energy, money to control the emissions from the chimney, which we should do. But at the same time, we should not forget that they are the other sources. So we should be sensitive not only to the emissions that is occurring from the chimney, but we should also be sensitive to emissions that occur from the fugitive in nature, which are from the handling of the raw material, handling of the your waste product, handling of your product, and transporting them, transferring them, storing them, and that sort of thing. And in fact, that emissions can become very large. So again, this is thing being shown, the estimation of the fly ash losses. You see here from the ESP, that is electrostatic precipitator, where we are removing the particles. So this is the clean, okay, clean air, and the particles from the this goes to the fly ash pond, but as it goes to the fly ash pond, there are the emissions which occur from here, as I shown in the last slide also. Okay, so fugitive emissions can be X was the total thing which was going on, Y is the gone to the ash pond, Z is gone to the chimney, but remaining portion, so the X was the total in, X is the input, this is Z is remaining, Y is disposed, okay, and whatever is the difference between the input and disposed, this will be the emission that is occurring from the bottom of the ESP. ESP is again a device to control the particulate matter. So again, this is how one can estimate the fugitive emissions. So let's also let me tell you that fugitive emission not only from the power plants you can do, you can also say what are the emissions likely to occur from the, let's say, a desert, because that is also source of pollution. So here the setup, what you see here is that it was a study done by the California Institute of Technology. What they have done is that they have put lots of samplers here. You can see the sampler here, you can see the sampler here, you can see the wind measurements. Let's say wind measurement, and here the dust sampler, and then this side also you can measure the dust, and you apply the models or different kind of models basically, and then you can find out what is the contribution from the entire region, how much will be the emissions from the desert, how much one can do the estimation, how much emission from desert or any process for that matter, which is more like fugitive emission rather than emission through the chimney. So what we have learned so far is that we can actually find out the emissions from the fugitive sources. One more example you see here, these are little measurements that was done. As I said, the wind speed, wind direction need to be measured, the concentrations are measured at the various sampling locations. Okay, so again this is sampler here, this is the source. Okay, it's basically repetition of what I have been saying, and then you can finally find out the Q. Okay, you remember we're trying to find out the Q, how we were trying to find out the C. C was known to us from the measurement. This was equal to pi u sigma y and sigma z. So just give you a real number which was done actually onto one of the power plants, and you can see the emission from the wagon tipper area. Let me say that to make it clear. The coal transfer. So you not only have learned the technique, but you also have seen that it can really be applied onto the field, and the measurements can be done. And these, depending on the number of hours of the operation, means the train is coming or the wagons are coming and they are being transported, and suppose the whole operation went on for, let's say, 8 hours, then you can find out what will be the total emission that is occurring from the unloading operation. So let's also remember that these are the not only causes the air pollution, but this is shear wastage of the product as well, shear wastage of the raw material, because coal is a raw material in the process. So finally, you can also, like, the interpretation was very important part, and always a person who gets a little feeling as to which is important when you start showing the things them in the relative sense, like absolute numbers sometimes people don't understand. So just for the example, for one study that was done, you see here the regular source from the chimney, because it was very highly controlled, okay, lots of money spent, ESPs and the back filters, and no one was there to take care of the fugitive source. And you see here the fugitive source was way high, okay, way high rather, and low. And you see here we spend a lot of money, but we have to be at least be serious. Well, the major problem is here. We have controlled this, fine, very good, but we also need to control this. And so that's why we would like to end this lecture saying that, well, look, the fugitive emissions are important, they need to be controlled, they have to be taken serious cognizance of that, and quantify them and see if they are important. If they are important, we need to control them. And just we don't need to control only the things which are going out from the chimney. What we need to control the emissions which are fugitive or the non-point emission, because sometimes they can be very large and they also impact immediately because they are all at the breathing level. We will talk about the air pollution from the sulfuric acid plant. As an important chemical industry, and sulfuric acid is used in many processes. This is raw material for many processes, and therefore we all over the country we find that sulfuric acid plants are there in all states, and in west of the industrial area you will find the sulfuric acid plant. So we'll go through the process of sulfuric acid and we see what are the sources, what are the operational parameters that govern the emissions from a sulfuric acid plant. Well, now what we'll do is we'll talk about the air pollution emissions from the sulfuric acid plant. Sulfuric acid is a very important chemical industry. In fact, the sulfuric acid is used almost in many processes which produce different chemicals. Sulfuric acid production is not a very complicated industry, so we will find that the distribution of the sulfuric acid industry is all over the country. Almost all our states will have a sulfuric acid plant, or in fact many plants would be there in industrial area. Even in you will find sulfuric acid plant even in some of the metallurgical processes units like the copper smelting, the zinc smelting. So apart from the sulfuric acid being produced as a raw material of sulfur, but this can also be produced from the metallurgical industries. So what we are doing now is that we'll talk about the air pollution aspects of sulfuric acid plant. So let's write this as H2SO4. Okay. The quick process, of course we'll go into the details of the process, because this industry, the emissions are almost fully dependent on how a plant is operated. So the basic principle of the H2SO4 production is the sulfur is burnt to produce sulfur dioxide, and then this is you are getting SO2, plus you get lots of heat, and that the amount of the heat is something like 127, close to 107,000 BTU per mole. Okay, that's a significant amount of the energy that you get from here. So this is the heat, or let's call this as the delta H. The next step is this SO2 that we produce must be converted into SO3. And this also produce heat, again let's call that as delta H, little less, but the amount is around 41,000 BTU per mole. The interesting part, or the heart of the entire sulfuric acid production, is this equation. And why we call it the important equation? Because this equation is reversible. So this can go to form the SO2 to SO3, and SO3 can also break down back onto the sulfur dioxide. So this step is what we call as the conversion step. Okay, so let's write this as the conversion step. Simple rule is high conversion less emissions. Okay, so if you are successful, in a way, if I can say it in the different words, if you are successful to make this reaction go forward, okay, that's where the success is from the air pollution point of view as well as from the production point of view. But the problem is, in order for this reaction to go forward, we need, in order for this to operate, we need to, in order to convert SO2 into SO3, we need good high temperature, or the higher the temperature, better is the situation, high temperature. And then this is we also need a catalyst to make this reaction go forward. This catalyst generally or normally this catalyst is vanadium pentoxide. Okay. The problem is, as you are seeing, that we need the temperature on this side, on the left hand side here. Okay. We also, but then we are getting lots of temperature here. So if we either we should consume the SO3 quickly, or if we are having a very high amount of heat, the reaction tend to go backwards. So the issues are, if we can say here that, well, somehow we must prevent backward reaction. Okay, and it's not simple actually, it's a challenge. It is a challenge. Why? Because on the right hand side, heat, if heat is not removed, right hand side you have lots of heat. Which heat I am referring to? I am referring to this heat. So if this heat is not removed, there is a possibility that equation can go backwards. And if I'm not removing the SO3, then also there is a possibility that reaction can go backward. And once it goes to backward, the SO2, if the portion of the SO2 which is not converted into SO3 have no other way but to be escape out as the pollutants. Let's also write that SO2, because this is what we should, SO2 not controlled or not converted, rather converted to SO3 will escape to the atmosphere as pollutant. Okay, and the next step is, once you have the SO3, is simply dissolve this SO3 or make it react with the water to produce the sulfuric acid. So if I can quickly remove this thing now, or let's write it here. So now this, we have got the SO3. Okay, this SO3 is reacted with the water, and it's very very quick and instant reaction, and then we can produce H2SO4. Okay, one more thing before we move to the next slide. Don't forget that this needs to be balanced. So this is 1/2. Okay. So what we have understood is, well, the conversion of sulfur to sulfur dioxide and sulfur dioxide to sulfur trioxide and sulfur trioxide, and the heat must be quickly removed, otherwise there is a fear, there is a possibility of SO3 decomposing back to sulfur dioxide, and if it does happen, the SO2 will be emitted as emission. Okay, so we want, idealistically, we want the reaction of sulfur dioxide to oxygen to continue to go in the forward direction, and that's what we'll see in the actual plant how this is done. I repeat that if something which is SO2 which is not converted into SO3 will escape, and that will be the pollution, and we want to prevent that. So let's go into the actual process flow sheet. So we are going to the actual treatment plant. Let's take a visit of the treatment plant, the sulfuric acid plant, as to how this works. So what you see here is the sulfur and the air, it is burnt. Okay, so this is the sulfur and the air is burnt in the boiler, in the kind of a combustion process, and it produces the sulfur dioxide, and the percentage of sulfur dioxide, this is important term here, is about 7 to 11% in the gases that is out from the furnace. Then immediate thing is to the heat is very high, and we want to reduce the temperature. So what we do is that we do the waste heat recovery, because we want to bring down the stream to the temperature which are more optimum for the conversion of SO2 into SO3, because the heart of the operation is conversion of SO2 to SO3. So we take it further for the conversion from the SO2 to SO3, but before that we bring down the temperature by the waste heat boiler or heat recovery, and you will see that we almost bring down the temperatures to around 470 degree Celsius. It's about that. Then we are passing through the converter. Okay, and you see here how the converter works is, you see here this is a converter tower, but the conversion is done in various phases. As you can see, first phase, second phase, third phase, fourth phase. The idea is that why we need to do in the phases. Okay, the phases is very important, because we have to make sure that the reaction is going continuously in the forward direction. So we must continue to recover the heat, else what will happen, if the heat is more, the reaction will go more towards the backward side, and SO3 will go back to SO2, and we will not get the SO3. So what you see here now, let's go back to the flow sheet. So this SO2 is, you see here the first pass. Okay, this SO2 is the first pass. First pass means it is immediately converted to SO3, and then immediately, once the conversion is done, before it can go back to sulfur dioxide, because remember that it can go back to sulfur dioxide, we quickly recover the heat. So once heat is recovered from the right hand side of the equation, if you recall, there is no possibility of whatever the SO3 that has been converted SO3 will not go back to SO2, but there is still some remaining SO2 is there. So we will again recover the remaining SO2 into various passes. Then you pass here in the second phase. Okay, and then again in the second phase the remaining SO2 will convert into SO3, and it will again produce a heat, and that heat must be recovered. The sign you see here, this kind of sign as you see here, is what we are referring to is the heat recovery. Heat recovery. Okay, so again it passed through the second stage of the conversion, and again the more heat is developed, because SO2 goes into SO3, this heat is recaptured, and then again you go to the third step, and then again heat is recaptured. So in the process we are trying to convert SO2 into SO3 at various stages, and in every stage when the heat is generated we capture the heat. So finally we bring it, so largely you see here most of the SO2 is converted to SO3 now here. Okay, and still the temperatures could be high, so we pass it through the economizer, bring down the temperature to around 185 to 250 degrees Celsius, and then now this is time to pass this SO3 to the absorbing tower and really produce sulfuric acid. So how it happens is that you are passing this SO3, the stream which is rich in SO3, to make the sulfuric acid. This is the reaction that you want that this to happen in here. So how this is done? We are not directly using the water, we are using the sulfuric acid. Okay, about 98 to 98% of sulfuric acid. And what is so specific about 98%, 99% is that you are recycling this acid, and we are using this acid to make the acid more and more concentrated. The point here is that at this condition, okay, the condition is what, 98 to 99% H2SO4. This is near azeotrope situation. Okay, what is that azeotrope situation is? Let's define. Azeotrope situation is a situation when the partial pressure in the liquid is the, for the various dissolved species, is the minimum. So when at this condition the partial pressure, see apart that there are many things in this one going, you see the SO3 is going, okay, the water is there, some water moisture can come, and there could be SO2. Okay, so we want the partial pressure of these things of these three species is minimum. We'll see if this is not minimum as to what possibly can happen. Okay, so this is continuously recycled, and you get and whatever is not absorbed in the tower and what is not converted into sulfuric acid, that goes out as the emissions, and that emissions are unconverted SO2, as you can see here, and some little acid mist that also can go with the atmosphere. And let me complete this picture. Okay, what else is happening here? As you are using this sulfuric acid, it is getting concentrated because it is dissolving more SO3 and reacting and forming the sulfuric acid. Once you are getting this required strength of the sulfuric acid, this is taken out, and this can be taken out, and this one stream can go as a product. Okay, you see here this is a product, and some portion of this one is taken to the absorbing to the air drying towers. You know, we are using the air in the process, the air was used, but where this air is coming from? Air is coming from after drying in the drying tower. So we use the sulfuric acid for drying the, so this is the stream which is going. So you recycle this sulfuric acid and keep on drying the air that you have. So here you have some, you may have some moisture here, but the thing which is you are going out is dry air. And it's very important to have the dry air in the process, and this is what is the dry air. We might even have it on the, this is what is the stream for the dry air. So now what you need to observe here is the conversion is important. We do the conversion in various steps to SO3. SO3 comes out, and at a particular strength of sulfuric acid is recycled, and more and more strength is sulfuric acid become more strength. Part of it goes to the as a product, and part of this can go the drying tower used to drying the air, because this air may have the moisture. If we had not removed the moisture, this moisture will be also be present here. Okay, and once the moisture is present, this moisture can escape from here, and it can quickly react with H2O and form the acid mist, and that acid mist also will go out from the absorbing tower. So as a result, you can not only will not only get the SO2 which is unconverted, and you will also get the acid mist. So the problem here is quite complicated, in the sense that we must operate every bit of the process very properly, and the attempt should be made as far as possible that there is no moisture that is present in here. So otherwise the moisture will also escape and forming the acid mist. Now the issue here is, can we improve the process? And this process is what we have seen as well, let's go to the back one. This process is called SCSA. What is SCSA? Single conversion, single absorption, because it is a single time we converted the sulfur dioxide into sulfur trioxide, and there was a single absorption here. So that's called SCSA. Now if we pay a little attention here, that if the conversion is poor, okay, if I could not convert SO2 into SO3, this is going to show up in the stack. Here you see here, you can read here, to stack unconverted SO2 and acid mist will escape. If I have any further opportunity to convert this SO2 into SO3, I think I would have done a good job, because I want to essentially control SO2, and the best way to control the SO2 in the sulfuric acid plant is to convert this into SO3. Okay. So, let us see how we can convert this into SO3. So, for that thing, the new method that has been developed, well, it is not new now anymore, but is called DCDA process. So far we knew the process that you see on your screen is that is we have understood from our first part, and that this part also we have understood. Okay. Now the question is, the last time when I was doing with SCSA, the emissions from the absorbing tower were put into the atmosphere. Here we are no more putting this to the atmosphere, but we are converting whatever was the SO2 that was left, okay, back into SO3, because unconverted, like this is the SO2 which remained unconverted, in which in my earlier process was going to the atmosphere. But what I am trying to do this time is to take this SO2 and convert it again into SO3, so that I am converting more and more of SO2 into SO3, and if I am able to convert more and more of SO2 into SO3, it means I am ensuring that SO2 emissions are smaller and smaller. So, in other words, I can say the emission of sulfur dioxide that will occur from a sulfuric acid plant is essentially function of non-conversion of SO2 into SO3. Okay. So, here I am taking this opportunity of remaining, whatever the remaining sulfur dioxide was there, I am taking it back and trying to convert this one. And remember here our thing was SO2 plus half O2, we were making SO3. Okay. And in order for this reaction to go forward, this is, if I am rich onto sulfur dioxide, my reaction will tend to go forward. Here I will again see my SO3 is gone here. So, I am again back to rich in SO2. If I am rich in SO2, I can again move it forward, and then I can produce more of SO3. So, that gives me the opportunity that I can again remaining SO2, which is richer now, because remember that SO3 is taken up in the absorbing tower in the form of sulfuric acid. The remaining SO2, so this stream which is coming out is again rich in sulfur dioxide. So, if it is rich in sulfur dioxide, I can make the reaction happen back in the forward direction and produce more SO3. If I am producing more SO3, it means I am decreasing the emission of SO2. So, if that is clear, now let us try to convert this SO2 here. So, the temperature here is a little low. So, we bring it here and make the stream little heat. What we are trying to do is we are taking a little heat from here and hotting up this SO2 here, and then okay, or rather making using this tower, which is not quite hotting up, but we will hot it up in the upper portion, and then you can see here that we take the little stream out from there, make it hot, okay, and pass it for the conversion. Now, you can see here the line which you see is going back to the converter, and now whatever the remaining SO2 was there, that will be converted into SO3, and that would come out here. And then once it come out here, we have to cool it, because in order for this to be able to be absorbed again the SO3 into the absorbing tower, we need to bring it down in the temperature. So, here what you do is you bring it down, and this is, you make it cold, and now here, so this was the heating part, this was the converting part, again cooling of the things, because now we want to take this one. So, again what I am getting here is the SO3. Okay. This SO2 which had become an excess, I converted it back to SO3. What it needed was to heat it up, then convert it, then cool it, because only the cool gases can go to my absorbing tower, and bring it to the next absorbing tower. And then the next absorbing tower, what I show is that whatever the SO3 now is converted into the final absorbing tower. And you will see here to stack is very, I'll use that word, very little. You can see a LE little SO2. A good job done, because I could convert the remaining SO2 back to SO3 and use that SO3 in absorbing and making a sulfuric acid. So not only I enhanced the value in the system by converting more and more of SO2 to SO3, and once SO2 is converted to SO3, the emissions will reduce significantly. So let's complete the picture here. Okay, that is similar to what we had done last time. Okay, so what we are really doing is converting the SO2 two times to SO3. First conversion route, and then whatever remaining, converting it again and absorbing it again. Okay, and then whatever the little thing which remained is sent back. So this process is called DCDA, double conversion, double absorption. But the focus for us has been as to how to reduce SO2 emissions. Okay, let's see what we have really achieved in terms of the pollution control, because the objective was to see the pollution control here. See here, this scale shows the conversion, and you see here the conversion, more and more conversion is occurring in this direction. Conversion of what? Conversion of SO2 to SO3. Okay, and you see here, if I was like operating at some percentage SO2, if I am able to increase the conversion, let's say that was, let's say you can read here is about 98% conversion, and suppose I could convert it to the 99.8%. So suppose this value is 99, let's say 99.8%. So when I did the double conversion, first conversion I was here, okay, and second conversion I was here. So corresponding emission, if you see here, after double conversion will be something like 2 pound per ton of H2SO4. If I was operating only at the single conversion, let's say, the emission would be like something like maybe more than like 30 kg, 30 lb, and this one is 99.8. So you can see the advantage of going to the double conversion, double absorption, and if this conversion is better, so we tend to all the time want to improve the conversion, and if the conversion is improved, your emission will reduce significantly, and that's how you operate the sulfuric acid plant. There has also been the technology to treat the sulfur dioxide that is emitted out from the absorbing tower, because it might still have some sulfuric acid. Sulfuric acid mist, of course, is there. Apart from that, you can also have the SO2. So people have developed the technology, but the fundamental remains, if we can convert the SO2 into SO3, the problem of SO2 emissions from the sulfuric acid plant is more or less handled. But still, if you want a very, very clean stack and you don't want any SO2 emission to go out, the technology has been developed by the oxidation of the sulfur dioxide with H2O2, and what you can see here, this process was developed to reduce the SO2 emissions. Dilute sulfuric acid and H2O2 are circulated over the packed bed in the countercurrent direction to the stream of SO2 containing the acetic acid. This is really what is happening in here. Maybe I can write the equation here. Is H2O2 here, you see here, plus SO2. H2O is a strong oxidizing agent, and it will make the H2SO4, and almost this SO2 will be taken care. Okay, sulfuric acid is absorbed in the solution where a rapid high yield reaction takes place to produce the sulfuric acid. That's what the reaction is. The acid produced in the scrubber becomes part of the plant's total production. So this is again part of the production. Let's not forget that the sulfuric acid will be is a product. It's not simply that we want to throw out the sulfuric acid. So this technology has been developed, but still I would rather say that it is a conversion, the success of pollution control, or let me use the success for the pollution prevention of the emission in the sulfuric acid plant is the how smartly you can convert SO2 into SO3. So before the next thing is well, the basic reaction I have shown you. Apart from that SO2, some of the acid mist, as you see here, will be emitted. Why the acid mist is emitted? Because for the two reasons. Suppose the partial pressure of the SO3 becomes higher in the absorbing tower. Okay, I am talking about the partial pressure. And suppose you also have the some moisture in the absorbing tower. So it can produce H2SO4, but this will be like a fine mist. And you can't control that, you can't stop that fine mist, and that will emit in the atmosphere. Okay, and sometimes the partial pressure of SO3 becomes higher even if there is no moisture. SO3 can as it is go out, okay, to the stack. Okay. So how we control the mist or the acid mist that has been formed? So you see here we are talking about the removal of the acid mist. Acid mist removal from the sulfuric acid plant is accomplished almost exclusively with packed fiber mist eliminators or demister's pads. What are really these? This although a small portion of SO3 that leaves the final absorber will be absorbed in fiber mist eliminator and the demister's pad, SO3 emission control depends primarily on the proper plant operation. That's we need to underline this. And what is the technology to remove the mist? As we will see here, poor sealing at the mist eliminator flanges that can lead to this, but I really want to show you is this as a process here. What you hear is this is the gas flow, okay, this is a wire mesh, and inside the wire mesh this is a fiber packing, okay, and then you pass the gas which is rich in acid mist, and then you have this fibrous pad here, and then the mist pass through this one. Mist is in the fine particles that will be trapped all over the place, and mist free air will go out, and then you can see, and these pads can be changed. In fact, if I can explain you, I mean it's something very simple. We see the desert coolers, you know, like we have the desert cooler in our houses. There's a pad here, and the water is falling on this one, and the grass is filled, something fiber material is filled, and the acid mist goes through this one, and then these are the stopped here. And then you can, the way sometimes we change the desert cooler, the packages, we can simply change this one, and whatever the mist that is collected here is also retrieved. Very quickly, it might be a good idea to give you a little feel about the SO2 emissions and the conversions. Suppose the conversion is, let's say, 90 SO2 to SO3 conversion, and here is the SO2 emissions. Emission, let me put with little arrow up there. So if you see here, if only 93% conversion is there, emission is around 48. And this quantity is in terms of the kg of SO2 per ton of acid. And suppose you are converting, let's say 94, then the emission could be around 41. And if you keep on improving your efficiency, and suppose you are producing 99.5, the emission of sulfur dioxide reduce so much that can become 3.5. If you further improve the efficiency of conversion of SO2 to SO3, let's say 99.7, this can even become around 2.0. Again, don't forget the units which I am referring here is kg of SO2 per ton of acid. Well, in summary, as I have been saying again and again, it is a conversion of SO2 to SO3 is a key process, and if we can handle that, then the SO2 emissions will significantly reduce. See, just again I repeat, very high conversion, the emission is very, very small. Similarly, the acid mist emission will again depend on how smartly you are operating your absorbing tower. So, this is how the emission aspects of sulfur dioxide, acid mist and SO3 from the sulfuric acid plant is there, and then whatever the acid mist that form can still be removed from the acid mist eliminators. I think we will stop there because this shows us about the details about the sulfuric acid plant.